we can keep expanding this outwards. And what we find, and this is going to be cool. I promise y'all that this is all worth it. Well, I think it is. What you find here is that this ratio, the larger the cube becomes, and we're going to go in a stylized way, the larger the animal, especially mammal, that's what I care most about, becomes, the lower the ratio of surface area to volume. Now, why would you care? This is so cool. I don't know why this isn't taught like in kindergarten. Actually, I probably can figure out why it's not taught in kindergarten. There are at least 3 predictions that come out of this. And there are 2 people who are associated with these rules, 2 people named Bergman and Allen. And there are 3 implications that come out of this relationship. Animal size, animal shape. Well, that's animal shape. That's amazing. And animal diet. So let's just pause here for a second. A simple mechanistic relationship between volume and surface area is going to allow me to predict in mammals the probable shape of that animal and what it eats. This is what is meant by cool science. So see how this works. Well, mammals in colder climates tend to have relatively larger bodies, because this allows them to minimize the surface area to volume ratio. Why would you want to do that in colder climates? Well, it's not the volume that's the relative. What is surface area going to cause to happen? Heat release. And if you can minimize the relative surface area, you can minimize the relative heat release. So what we have here is that mammals in colder climates try and minimize the amount of heat release by tending to be larger. It's not perfect. It's not a perfect correlation, but it's certainly enough to where you're like, that is kind of cool, kind of cool. It allows us to do this. Second, animals living in warmer climates will tend to be longer versus spherical, and this is going to allow also for the ventilation or retention of heat. So you can go across the globe, and let's say you're looking at humans. This is true in humans. The Bergman and Allen rules hold in humans that if you were to go towards equatorial Africa, people tend to be relatively more cylindrical. We call them tall. But that's, it's not quite as offensive as what the Inuit get called. They get called spherical. Pleasantly spherical, I suppose I could say. Yeah, she is definitely pleasantly spherical. Now, it's not perfect, but you probably never realized there was this relationship across the globe. It's kind of cool. For free, we can get a third prediction out of this before we get to diet. Think about animals living in cold climates versus animals living in warm climates. If you're a cold climated animal, do you want long floppy ears? Why not? They just basically are like, heat, go away. And what you actually find is animals in colder climates tend to have shorter appendages. Ears, legs, and so forth. So if you look at a cold climate hair versus a warm climate hair. Now notice that this isn't mechanistic. It's not perfect. It's not everyone who lives in warm is tall, and everyone who lives in cold is spherical. It's probably like the worst compliment you give someone. Did I gain weight? You're definitely more spherical than you used to be. But these sort of, we can see how we started with straight mechanistic to now we're getting more implicational. We're getting more where there's trends and there's tendencies that are useful for us. This can also help us explain, by the way, the elephant. Anyone know why the elephant has huge ears? Yeah. Well, it doesn't fan. It's not acting as a fan for it. There's a lot of blood vessels in the ears of the elephant, and it's waving them around, releasing heat into the environment. So it's not fanning itself.
Oh.
I mean, that'd be awesome if it did, though. That would be really cool. I mean, I would like that. Because I would have an elephant. It'd be cool to have a built-in fan. It's like, oh man. Any question about these? These are cool. These are straight biological principles. Well, what about food? So this is going to allow me to predict some behavior. This is what's really cool is I can start with strict biology and make behavioral predictions in my animals. So here's how this is going to work. Larger animals are going to preferentially use different types of food sources than smaller animals. So that's how this argument is going to run. In mammals, the metabolic rate gets lower in larger mammals. That is, the metabolic rate is higher in smaller animals. While you're writing that down and thinking about what that means, we want to use our terminology, so I need your clickers. In mammals, so we're going to have size, and we're going to have metabolic rate. Is the relationship between these two positive, A, negative, B, or all we have is none, C? With this sentence, what is the correlation between, oops, sorry, I don't know what that just did. An unexpected error occurred. Okay, I don't know what that unexpected error is. It doesn't want to go. It doesn't want to let me do anything. It's like, okay. It's like, send report. No. Boy, it is really like, it's really like, it really doesn't want to, it doesn't want to move, it doesn't want to do anything. It's like, we don't care about metabolic rate and, is it positive, negative, or, it says unexpected error, I swear. Let's go at 5, 4, 3, 2, 1. What's the correlation? 3, 2, 1. What's the correlation? Most of y'all got this right. Yes, it is a negative correlation. One goes up, the other goes down. In other words, you don't have to write this down. This is going to be in the notes. But a smaller animal has a higher metabolic rate than a larger animal. Like much larger. Well, what this means here, and this is really in the interest of time, the upshot of all of this is that smaller mammals are more likely to base their diets on rarer, high-energy food sources than our larger mammals. What is a rare, but certainly higher energy food source? You think about what do small mammals tend to eat? Nuts. You're a little smaller. They're things that are living. They're animals that are living. Bugs. Yeah, they do eat nuts and stuff like that, but they also eat bugs. We call them insectivores because they base their. And actually, when you look at the data, I'll just show you really the main thing here is this Jarman-Bell principle, which gives us a prediction of how animals are going to eat. And here's what's cool: is that that's true. But you got to sort of appreciate what we've done in the past 50 minutes. I've taken you from a very simple idea of a cell and just said, working step by step, can I explain how the brain is organized? Can I explain surface area to volume and mammal differences across the globe? Can I predict dietary differences? It's pretty good. This is, I think, kind of amazing. Now, next week, what we're going to do is we're going to take biology and go, can I predict, let's see. Can I predict who's going to mate with who based on biology?
Yes.
I don't know yet. I haven't seen those notes. Y'all have a great weekend.